Recall the Thom's algorithm for multiplication of numbers that we have just studied. So the idea of the algorithm was that we convert the problem of multiplying two numbers into the problem of multiplying two polynomials. And in slightly different notation, we had two polynomials p prime and p double prime, both of them of degree k minus 1. So we have computed their values in 2k minus 1 convenient points, and then we multiplied the values of these polynomials in each of the points to get the value of the product of the polynomials in all of these points, which we then used to interpolate and get the polynomial itself, so to get all the coefficients of this polynomial. And this is the crucial step, the interpolation, although the recursive complexity of the algorithm was basically determined by this step, but the idea of interpolation was crucial still, and it is interesting how fast can we interpolate the polynomials. In Thom's algorithm, that was not a great deal because our degrees of the polynomials were fixed. So this parameter k was fixed, it was constant, and anything depending solely on k was thus constant. But what if we now make k a variable as well, a variable parameter, and how can we determine the complexity of interpolating a polynomial of given non-fixed degree? So let's now consider an algorithm of fast Fourier transform that we can use to actually perform the interpolation in time, which is big O of k log k, assuming that we are able to do each operation on coefficients of the polynomial in constant time. So now we'll move away from bit complexity and we'll move on to the problem of interpolation. The algorithm that we'll now talk about, the fast Fourier transform, is actually tightly connected with both interpolation of polynomials and simultaneous computing of the value of a polynomial into the algorithm of fast Fourier transform that we'll now discuss actually is tightly connected to both polynomial interpolation and to simultaneous computation of values of a polynomial in a set of points. And we'll start with the latter problem. So let's assume that we have a polynomial p and that we'd like to calculate the value of the polynomial in several points. We'll assume that we'll have n such points, and we'll also assume, for the latter simplicity, that n is a power of 2. In what follows, we'll treat each arithmetic operation on coefficients of the polynomial or on the value that we substitute for a variable x as a single operation. We'll not discuss bit complexity, and actually we'll work even possibly with real numbers and even possibly with complex numbers. So each arithmetic operation on numbers would be counted as a single unit time operation. Now let's see how many operations we'll need to compute the values of the polynomial. So even if we use Horner's rule for computing a single value of polynomial p, that is taking c0 times x to the power of 0 and taking x out of all other terms, and then here we get the sum for g from 1 to n minus 1, c j x to the power of j minus 1, and if we then repeatedly expand this thing, we get an expression which corresponds to Horner's rule of computing value of the polynomial. How many operations do we have here in this formula? Well, we have linear number of operations on n. A single operation is an addition or multiplication of numbers. So thus, to compute these n values, to evaluate polynomial at n points, we'll need n times big O of n operations, and that's quadratic number of operations. So let's see if we can do the same simultaneous computation faster. To do it faster, we need a special set of points though. Well, assume that we have among our points half of them being equal to minus the other half of the points. So say tau n over 2 is equal to tau 0 with minus, and so on. Tau n minus 1 is equal to minus tau n over 2 minus 1. So the second half of the points is minus the first half of the points. Then if we choose our points this way, we can apply divide and conquer approach in the following way. Our polynomial value on points tau I, where I is less or equal than n over 2 minus 1, will be computed as, and the polynomial value at the point tau I plus n over 2, if we remember about these relations between our points, would be computed as c0 minus c1 tau I plus c2 tau I squared minus c3 tau I cubed, and so on. So now we see that actually these polynomials have lots of common things between them. So that if we mark all the even summands here in one polynomial, sub-polynomial, and all the odd sums here in the other polynomial, we have the following. So let's introduce two new polynomials, p0 of x as c0 plus c2x squared plus c4x to the power of 4, etc., and p1 of x of this form. So now we can express the value of our polynomial p at the points tau I and tau I plus n over 2 through the values of these polynomials just in the point tau I. And we'll do it like this. And now we shall reduce the degree of these polynomials for our divide and conquer approach to work. Currently, these polynomials have fewer terms than p, but their degree is practically the same. But we will effectively halve their degree. To do this, we note that all the degrees of x in p0 are even, and let's just halve each of them. Instead of x squared, we have x to the power of 1. Instead of fourth power, we have the square. But then we have to substitute tau I squared in this polynomial so that our formulas still work. For p1, we cannot perform this trick because the degrees are odd, but we can make them even by taking x out of the polynomial. So let's divide all the terms by x, thus getting this polynomial, but then we'll have to slightly alter our formulas so that now we'll have to multiply by tau I here. And now we can take all these terms and half the power of x, and of course then we have to have tau I squared in these two places. But now the degree of each of these polynomials does not exceed n over 2 minus 1, and so we can now try to apply divide and conquer approach. So now let's t of k be the time or the number of operations that is needed to perform the evaluation of a polynomial of degree at most k minus 1 on k points. If we believe that we can perform the evaluation of our polynomials p0 and p1 at these types of points, and recall that we need just half of them so that I does not exceed n over 2 minus 1. So to evaluate our p at n points, we need to evaluate this guy at n over 2 points, evaluate this guy on n over 2 points, and also perform these additional tasks, and the number of these tasks is linear. So that we have two sub-problems of evaluating polynomials of degree at most n over 2 minus 1 on n over 2 points. So our assumption is that it can be done in this time, and plus big O of n operations for this part of the computation. So if this works out, then the master theorem will tell us that t of n is big O of n log n. And this is great improvement over quadratic complexity of evaluating a polynomial at arbitrary endpoints. But here's a caveat. For this to work, we need for this function to be bounded by the same kind of recursive bound. But then we need the points that we insert into p0 and p1 to follow the same rule. So half of these points should be the negations of the other half of the points. But now, if we take positive and negative numbers, for those, we evaluate p0 and p1 only on the squares of these numbers. And thus, it seems that everything breaks because squares of numbers are always non-negative. And we cannot split all these squares into two halves. But here, complex numbers help us, because complex numbers need not necessarily obey the same rules as real numbers when we square them. And that's exactly what we'll now do. So we'll choose our set of points, tau 1 through tau n minus 1, as special set of complex numbers, so that they can be split into such two halves, but their squares have the very same property. And then everything will work out.